are going to see about architectural and operating system support for system called security. Introduction. Protecting the operating system kernel is significant concern given its capability and shared nature. In recent years there have been reports of number of security attacks on the OS kernel through system called vectors, a popular technique to protect OS kernel against untrusted user process in system call checking. Idea is so limited system call that given process can invoke at runtime well as the actual set of arguments value used by system call. The technique is implemented by adding code of OS entry point of system call. The code compares incoming system call against list of allowed system call and argument set of values. The whole modern OS provide kernel support for system call checking. Linux Kecom security commuting module is the most widely used implementation of system call checking. Overheated of system call and argument value checking is especially considering the application with high performance requirements such as conserve the environment and the overhead. One of the key of highlighted virtualization. The overheated of system call plus checks macro benchmark 40%, micro benchmark 25%, accepted future checks 21% to and 42%. In this paper, we present both software and hardware implementation of Darko. And next, see the hardware implementation of Darko introduction novel eliminate particularly all of the checking overheated. System call Luckiest side buffer SLB and keep recently validated system calls and system call target buffer STB to reloaded the SLB in advance. In our evaluation, we execute respectively workloads in Docker containers. We run Kecom on Intel Exxon Surveyor, checking both system call IDs and arguments value. Find that with Setcom, the average execution time macro and micro benchmark 1.414% and 1.25% higher. Overall, the system call checking overheated for various Setcom and new Darko architecture and caches validate system call IDs and arguments value for use and evaluation of the software and hardware implementation of Darko. To see background system call interface OS kernel exposed to the user space in x86 and 6435. A user space process recurs a system call by using system call instruction. Next is system call checking, a core security technique to protect the OS kernel against untrusted user processes. System call checking. See the figure. The figure shows an example system call check in user space is kernel space and process first line, second line, move F and move system calls and the example of the program loads the system call arguments and ID, registers RDA and REX respectively, performs the system call. This ID corresponds personality system call and the ID is argument value is allowed. It is the allowed. Let's system call execution to proceed. Base line 8 is explains it is terminate the process. Line 11. Profile is long list of if statements there are executed in sequence. Finding the target system call and target combination of arguments values in the list can take long time. So, in the region for the often high overall Setcom. Setcom does not check the values argument, they are pointers. This is because such a checks does not provide any protection. A malicious user could change the contents of the location point. So to be after the check, creating time of check time of use. TOCTU attack 37 and 38. Simply check system call IDs and argument values based a white list of extract IDs and values 19, 39 and 43. System call checking in modern systems. System call checking in Setcom being performed in almost all the modern Linux based system interface and this includes modern container and lightweight VM runtimes such as Dr. Google Visual, Amazon Free Cracker and Other environments such as Android and Chrome OS also SECCOM 15, 44 and 46. Next, SECCOM profiles. In this paper, we focus on container technology which have both high performance and high security requirements. Docker default profile allows 358 system calls and only checks 7 unique arguments values of the clone the personality system calls. Other profile include the default wizard profile, which is a 74 system call 130 arguments checks. Also the profile for AWS Firecracker Micro VMS contain 37 system calls and 8 arguments check 20. In this paper, we also explore more secure SECCOM profiles targeted for some application. Application specific profile are supported other projects 17, 24, 50 and 53. Threat model. We adapt the same threat model is executing system call checking systems such as SECCOM, where untrusted user space process can be adversable and attack of the OS kernel in the context of application or deployed in the cloud and OS kernel it has you attack mirror work 54 and 56. Airco provides both high performance and high level security. Studying overhead locality to motivate our professional, we benchmark the overhead of state of the art system called checking. We focus on understanding the overhead of using generic system called profiles, using smaller and application specific system called profiles, and using profiles that also checking system called argument methodology. Insecure SECCOM is displayed. It is insecure baseline where no check are performed. Dr. Default SECCOM profile. It is automatically used all decor, contents and other containers technology. System called no argument. Application specific profiles without argument checks where the filter whitelist to the exact system call IDs used by the application. System call complete. Application specific profiles with argument checks where the filter whitelist the exact system call IDs and stack arguments value used by the application. System call complete 2x. Application specific profile the constant of running the above system calls complete profile to in a row, and hence the profiles perform twice the number of checks as system call complete. The goal it is model a near future environment that performs more extensive security checks. Execution overhead. Figure 2 shows the latency and execution time of the workloads using the 5 tips of SECCOM profile described in section. Workload the result normalized in insecure. The overhead of checking system call IDs. To assess the overhead of checking system call IDs, we compare insecure to Dr. Default. Figure 2 encloses SECCOM using Dr. Default profile. Increase the execution time of macro and micros 1.05 and 1.12 on average respectively. Overall average performance overhead using system called no argument profile is 1.04 and micro benchmark 1.09 for micro benchmark respectively. Overhead of checking system call argument. To assess the overload of checking system call argument, we first compare system call no arguments and system call complete. The number of system calls in these two profiles in the same, but the system call complete additionally check argument values. We can see that checking argument brings significant overhead, and the average executed time 1.04 and 1.14 and perform 1.09 and 1.25 respectively. We now double the number of checks by going from system call complete and system call complete 2x. And Next is the system call locality. We measured all the system calls and argument issued by our macro benchmarks. Figure C, so frequency of the top calls which together amount for 86% of the calls. See figure 3, frequency of the top system call and average U distance collected from the macro benches. We see that system calls high localities, 20 system calls account for 86 of all the calls. For individual system calls are often called with three and different argument sets. The figure 3 is explain that the average distance is often only a few tens of system calls, indicating high locality in reusing system call checking result. Darko system call checking. To minimize the overhead of system call checking, this paper proposes a new architecture called Darko. Darko always execute the many if statements and Secco profile it every system called figure 1. Next see the figure 4 workflow of Darko system. First you see system called argument 1 and argument n. The next check table. Check table is present. Yes, you executed X is correct. You executed the proceed with the system call. No, that is the print is execute the system seccom profile and yes update table and allowed yes is update table, no terminate user program. Next is checking a system call its argument. SID valid base and argument bit mask. Argument 1 and argument 2 selector. Software validate argument table VAD validate argument sets. So H1 is connected to the selector and argument 1 and argument N2 connected to the selector. The selector is connected to argument bitmarks. The base is connected to the base of the save system calls in validate argument sets. Checking system call IDs only if we only want to check system call IDs. The design is simple. It uses the table called system call permission table SPT. The valid of this is single bit. Next see checking system call arguments. To check system call arguments we engage the SPT and couple the software structure called validate argument table VAT. Both SPT and VAT is private process. So the same both software and hardware implementation of Darko. 5 shows the structure. The SPT is still indexed with SID. And next see a software implementation. Darko can be completely implemented in software. Both the SPT and VAT are software structure in memory. We build Darko as a Linux kernel component. In this OS kernel at the entry point of system call, we insert instruction to read SID argument set of values. Darko uses SID to index into the SPT and bit. If argument checking is Darko further takes correct bits from the argument to perform and read VAT compares the argument value decided whether the system call pass or not. Initial hardware implementation. Initial hardware implementation of Darko Max SPT hardware table in each row. The VAT remains a software structure in memory. The checks can only be performed when either SID or both the SID and argument set of values are available. See Darko hardware implementation. In the initial hardware implementation of section, VD has shortcoming that it requires memory access to read VAT. In fact, 2 accesses, one for each of the hatch function. First one is catching the result for successful checks. There, reduce the overhead of system call checking. Darko introduced a new hardware cache recently. Valid system call argument sets. So the cache is called system call look side buffer. It is inspired by TLSP translation look side buffer. The finger 6 is so SLB. It is indexed with system call SID, the number of argument that is required. The design minimizes the space needed to cache arguments. Each has an SID field, valid bit, hash field, and valid it argument set denoted. Figure 7 describes the SLB operation performed by Darko, SPT, and VAT. And next see preloading argument set. The SLB can significantly reduce the system call checking time and caching recently validate arguments. Fundamentally, the STB operators like BTP, while the BTP products target location, the upcoming branch will jump to the location in VAT that stores the valid argument set. Upcoming system call will require. Next see system call target buffer and operation STP. In figure 8, each entry stores the program counter BC of system call, valid bit, and SID of the system call hash field. The later contains one cache value, two possible that arguments. These arguments set from VAT when the entry was loaded into STB. System call target buffer structure. The preloading operation into SLB shown figure 9. As soon as POS instruction inserted in the ROP, Darko uses its BC to access STB. After the time system calls is not the ROP hit and the actual arguments may be not ready yet. Putting it all together, figure 10 shows the Darko hardware implementation in bold horse shape. The 3 core hardware tables SLB and STB, SPT, 8 KB, 4 KB and 4 KB. It is that the SLB information is backed up in the per process after VAT in memory. VAT entries are loaded into the SLB demand by hardware and provides an SID and SPT, which takes SID provides its arguments count and its VAT location. Darko execution flow. Table 1 shows the possible Darko execution flows. And flow occurs when the STB access, SLB preload, SLB access all hit. Flow 2 occurs STB access, SLB preload hit. Table 1 possible Darko execution flow. The slow case can different, let's see, depending on whether the VAT access hit miss in the cache. If the VAT does not have reduced entry, OS is invoked and execute execco filter. Implementation as the invention of software checking, data coherence, content switches, and simultaneous multi-threading support. Generally of Darko discussed so far present a Darko design that is broadly compatible with Linux scope. So we could describe all system solution in practice. It is easy to apply Darko ideas to other systems called checking mechanisms such as OpenBSD, Blush and DAMI 12 and 13.
Security issues. To understand the security issue in Darko, we consider two types of side channels. These in the Darko hardware structure and those in the cache. Darko hardware structure could presently provide side channels due to two reasons. One is Darko uses specialized assets preloads the SLB before the system call instruction reaches. And second one, the Darko hardware software structure are shared by multiple processes. Loads, we use 15 workloads split into macro and micro benchmarks. System call profile generation, they are number of ways create application specific system call profiles using both dynamic and static analysis. Second, you see modeling the hardware implementation of Darko. We use cycle level full system simulates to model server architecture with 10 cores and 32 GB of main memory. Evaluation, performance of Darko. Darko software implementation figure 11 shows the per performance workloads using the software implementation of Darko. System call no argument, system call complete and system call complete 2x. Figure 12 latency and execution time of workloads using hardware implementation of Darko For each workload, the result normalized in insecure. Hardware structure hit ration. To understand hardware Darko performance, figure 13 shows hit rates of STB and SLB structure. For the SLB, we show two bars, access and payload. SLB access occurs when the system call it is head of the ROP, and SLB preloaded occurs when the system call is inserted in ROP and SOP is looked up. And SLB preload is hit means only that the SLB likely contains discrete entry, and SLB preload triggers a memory request preload the entry. Darko hardware implementation figure 12 shows the workload performance using hardware implementation of Darko. The figure shows insecure and hardware Darko running the SecComp profiles from section 4A, namely system call no argument, system call complete, system complete 2x. Next see Darko resource overheated hardware components, hardware Darko introduction 3 hardware structure SPT, STP, SLP. It is like a CRCH generator. See, assessing the security application of specific profile, we compare the security benefits of application specific profile. Recall that system call complete checks both call IDs and arguments, while Docker default only checks system IDs. There is the fraction of about 20% remaining in dark color that required by the container runtime. Note that zone section while application specific profile is smaller. SLB sizing figure 14 uses violin pollet illustration that probability density of the number of argument system call, the first entry corresponding in completing Linux kernel system call interface. Figure 15 security benefits and application specific profile over the default Docker profile. 16 latency and execution time workloads using different profile. For each workload, the results are normalized insecure. This experiment uses older CentOS 7.6 1810 with Linux 3.10. Latency execution the workloads using software information of Darko. Others environment for each workload, the result normalized into insecure. This experiment uses the older CentOS 7.6 1810 with Linux 3.10. Other related work, there is the rich literature on system call section 93.1.104 yearly implementation based on kernel tracing 93.99 in Cure executes performance Bentley as very system call is penalized by the latest 2 additional context switches. CHERI 108 and 1110, CODOMS 111 and 112, PUMP 113, REST 114. The acknowledgement of this work were funded by what of NSP undergrad CNC 1956-007 CNX 7 CCF 1725 734 CCF 1816 615 CCF 2029 049 and gift from Facebook.